Good morning, Dean. Good morning, classmates. I am Catherine Capa, and together with my partner, Ma'am Mariluz Pandilio, we will be presenting Chapter 6, which is about databases and information management, the basis of business intelligence management. For our course intended learning outcomes, after completing this chapter, we would be able to answer the following questions. 1. What are the problems of managing data resources in a traditional file environment, and how are they solved by a database management system? 2. What are the major capabilities of database management systems or DBMS, and why is a relational DBMS so powerful? 3. What are some important principles of database design? 4. What are the principal tools and technologies for accessing information from databases to improve business performance and decision-making? And lastly, why are information policy, data administration, and data quality assurance essential for managing the firm's data resources? We will start with organizing data in a traditional file environment. Let us first define what is traditional approach to data management. It is an approach whereby separate data files are created and is stored for each application program. To have an effective information system, users should be provided with information that are accurate, timely, and relevant. Accurate information is free of errors. Information is timely when it is available to decision makers when needed. Information is relevant when it is useful and appropriate for the types of work and decisions that require it. It may be a surprise knowing that a lot of companies don't have timely, accurate, and relevant information because the data in their information system has been poorly organized and maintained. That is why data management is very important. To better understand the problem, let us analyze how information systems arrange data in computer files in a traditional file management. File organization terms and concepts. A computer system organizes data in a hierarchy. Let's use this student's course file as an example. The data hierarchy starts with the bit. It is the smallest piece of data that a computer can handle, and is represented by a 0 or a 1. Bits can be grouped to form a byte. Byte is a collection of bits that stands in for a single character, which could be a letter, a number, or another symbol. Bytes can be grouped to form a field. It is a collection of characters that form a word, a collection of words, or a complete number, such as a person's name or age. Next is the record, which is a group of related fields such as the student's name, their course, the date, and their grade. Here in record, an entity is described. An entity is a person, place, thing, or event that is the subject of information being kept and preserved. Each property or characteristic that characterizes a specific entity is called an attribute. For example, the student ID, course, data, and grade are the attributes of the entity course. The specific values that these characteristics may have are written in the fields of the record that represent the entity course. These related records can be collected to form a file. And lastly, these related files can be organized to form a database. In our example, a student database might be made by combining the course file with files on the student's financial and personal backgrounds. Now let's go to the traditional file processing. In the majority of companies, systems developed on their own in the absence of a corporate strategy. Each business, such as accounting, finance, manufacturing, human resources, and sales and marketing, set up its own systems and data files. The typical method of information processing is this traditional file processing. Each application requires a unique data file that is likely to be a subset of the master file. Obviously, each application required its own files and software to operate. The use of a traditional approach to file processing encourages each functional area in a corporation to develop specialized applications. Each application requires a unique data file that is likely to be a subset of the master file. These subsets of the master file lead to the traditional file environment controversies. First is the redundancy and inconsistency in the data. Data redundancy is the presence of identical data in numerous data files, resulting in the storage of the same data in multiple locations. Data redundancy occurs when different groups of a company get the same piece of information and store it in different locations. Data redundancy wastes store space and can result in data inconsistency. It is where several values may exist for the same property. Second is the program data dependence. It is the relationship between the data that are kept in files and the particular programs needed to update and maintain those files, making it necessary for data changes to occur when programs are changed. Every traditional computer program must specify the location and nature of the data it employs. Any change to a software program in a traditional file environment could need a change in the data that program accesses. The third problem in a traditional file environment is not being flexible. After substantial programming, a typical file system can produce routine, scheduled reports, but it cannot produce ad hoc reports or promptly address sudden requests for information. Information needed by ad hoc queries may be stored elsewhere in the system, and retrieving it may be too costly. Several programmers may have to work for weeks to put all the needed data into a new file. Next is the lack of security. Here, information access and distribution may be out of control because there is minimal data management or control. It's likely that management has no method to track down those who access or even modify the company's data. Lastly, the data availability and sharing issues. Because pieces of information are stored in different files and parts of the company, it is hard to share or get information quickly. Different functional areas or portions of the organization cannot communicate freely with one another. If users see conflicting values for the same piece of information in two different systems, they may opt not to use the systems because they cannot trust the reliability of the data. Let's now proceed with the data management using a database approach. Many of the problems associated with traditional file organization are addressed by a database technology. So what is database approach to data management? It is an approach whereby a pool of related data is shared by multiple application programs. For example, a business could build a single shared human resources database instead of keeping employee information in different information systems and different files for people, payroll, and benefits. Next is the database management system. But before, let's have first a more detailed definition of database. A while ago, we have said that database is a group of connected files. Particularly, database is a collection of data that has been centrally located and controlled to effectively support several applications. Now, let's define database management system. Database Management System or DBMS is a software that enables an organization to consolidate data, manage it effectively, and give applications access to the data contained in the system. The Database Management System connects application programs to actual data files. When an application program asks for a piece of data, like gross pay, the DBMS finds it in the database and shows it to the application program. Unlike when using traditional data files, the programmer had to notify the computer where each piece of data was after giving its size and format. The DBMS frees the programmer or end user from having to comprehend where and how the data are actually kept by separating the logical and physical views of the data. The physical view demonstrates how data are actually arranged and structured on physical storage media, while the logical view depicts data as they would be seen by end users or business specialists. The database management software lets users get to the actual database for the different logical views they need. Now let's take this human resources database with multiple views as an example. A single human resources database provides many different views of data depending on the information requirements of the user. Illustrated for this database are two possible views. One of interest to a benefits specialist who might need an employee's name, social security number, and health insurance coverage among others, and one of interest to a member of the company's payroll department who might need to know the employee's name, social security number, gross pay, and net pay. All of the information about these views is saved in one database, which makes it easier for the company to handle them. So how a DBMS addresses issues with the conventional file environment? A DBMS reduces data redundancy and consistency by cutting down on the number of separate files where the same data is repeated. Even though the company may not be able to get rid of all redundant data, the DBMS can help control it. Second, using a DBMS can aid in ensuring that all instances of the data have the same values even if a company retains some redundant data. This eliminates data inconsistency. Third, the DBMS separates data from programs, allowing data to exist independently. Because users and programmers can run ad hoc queries on the database's data, access to and availability of information will go up, and the cost of making and keeping programs will go down. Lastly, DBMS enables the organization to centrally manage data, their use, and their security. So modern DBMS use various database models to keep track of entities, properties, and relationships. The relational DBMS is currently the most common type of DBMS for PCs, as well as for bigger systems and mainframes. Relational DBMS displays data as two-dimensional tables called relations or files. Each table includes information on an entity and its characteristics. Examples of these are DB2, Oracle, Microsoft SQL Server for large mainframes and mid-range computers, Microsoft Access for desktop system, MySQL for well-like open source, and Oracle Database Lite for mobile computing devices. Here is an example of a relational DBMS. In the database, the entity's supplier and part each have their own tables. Each table consists of a grid of informational rows and columns. Each field is a characteristic of that entity, and each unique piece of data for each entity is saved as a different field, which can also be called a column. A row in a table represents the actual information about a given supplier. Rows are rows, sometimes known as records or in more technical terms, tuples. Next is the relational DBMS operations. If two relational database tables share the same piece of data, it is easy to combine them to give users the information they need. To construct usable data sets in a relational database, three fundamental operations are employed, that is select, join, and project. All the records in the file that meet the given criteria are created as a subset by the select procedure. Select, in other words, generates a subset of rows that satisfy specific requirements. For example, in this illustration, we want to choose records as rows from the part database whose part number equals 137 or 150. Relational tables are joined together to give the user access to more data than are contained in each table alone. In our example, we wish to combine the supplier table and the reduced part table. only parts 137 or 150 will be shown into one new table. The project procedure generates a subset of the table's columns, enabling the user to construct new tables that only include the necessary data. In this case, we only want to extract the part number, part name, supplier number, and supplier name columns from the new database. Cloud-based databases and non-relational databases. Cloud-based databases are database service built and accessed through a cloud platform. It organizes and stores structured, unstructured, and semi-structured data, just like traditional on-premises databases. It provides many of the same benefits of cloud computing, including speed, scalability, agility, and reduced cost. Examples of these are Amazon Relational Database Service and Microsoft SQL Azure. While non-relational databases use a more adaptable data architecture, which are built for managing big data sets across numerous distributed machines and for simple scaling up and down. Businesses are turning to NoSQL non-relational database systems for cloud computing, unprecedented data quantities, and massive workloads for web, because they can speed up basic searches on huge amounts of structured and unstructured data like web, social media, graphics, and other types of data that are hard to look at with traditional SQL-based tools. Examples of these are Oracle NoSQL Database and Amazon SimpleDB. DBMS capabilities. A DBMS facilitates the management, accessibility, and organization of data in a database. The data definition language, data dictionary, and data manipulation language are the most important. Data definition language is a feature of DBMS that specifies the structure of the database's content and is used to create database tables and specify the properties of each table's fields. Data dictionary is a human or automated file that contains descriptions of various data components and their properties. A basic data dictionary feature shows the name, description, size, type, format, and other characteristics of each field in a table as shown here in our illustration. Data manipulation language is a specific language for navigating and modifying data in databases, which allows users to add, modify, delete, and retrieve data from a database. The commands in this language enable programmers and end users to extract data from databases in order to build applications and respond to information requests. The most well-known language for data manipulation today is the Structured Query Language or SQL. Here is an example of an SQL query illustrating the SQL statements for a query to select suppliers for parts 137 or 150. As you can see, they produce a list with the same results as with our example a while ago, showing the tables for the three basic operations of a relational DBMS. SQL is also used by Microsoft Access. Using Microsoft Access features, users can conduct queries by specifying the tables, fields, and results they desire, then selecting the rows from the database that meet specific criteria. These subsequent actions are converted into SQL commands. This is an access query illustration which shows how the SQL query to choose suppliers and parts would be created using the Microsoft Query Building tools. Now let's move with creating a database environment or the database design. Before you can make a database, you need to know how the data are linked, what kinds of data will be saved in the database, how the data will be used, and how the business will need to change to handle data from a company-wide point of view. The database requires both a conceptual and a physical design. The physical design of a database depicts how the database is actually set up on direct access storage devices, while conceptual or logical design of a database is an abstract representation of the database from a business perspective. To use a relational database model efficiently, complex data groups must be reduced to eliminate redundant data pieces and uncomfortable many-to-many relationships. This is done by normalization. It is the act of taking large complex collections of data and turning them into manageable, flexible, and adaptable little data structures. Let's take a look at this illustration of an unnormalized relation for order before normalization. An unnormalized relation contains repeating groups. For example, there can be many parts and suppliers for each order. There is only a one-to-one correspondence between order number and order date. Now, here is an illustration of normalized tables created from order. The relations shown in here result from normalizing the relation order step by step. After normalization, the original relation order has been broken down into 4 smaller relations. The relation order is left with only 2 attributes, and the relation line item has a combined key consisting of order number and part number. Relational database systems attempt to enforce referential integrity rules to maintain consistency in the relationships between connected tables. You can't add a record to a table that links to another table with a foreign key unless the linked table already has a record with the same name. Then we have the Entity Relationship Diagram or ERD. It is used by database designers to describe their data model. Here is an example of an entity relationship diagram. This diagram shows the relationships between the entity supplier, part, line item, and order. The boxes represent entities. The lines linking the boxes represent relationships. A connecting line between two things that ends in 2 short marks indicates a one-to-one relationship. A one-to-many relationship is indicated by a line connecting 2 objects that ends with a crow's foot and a short mark on top. Improve business performance and decision-making by the use of databases. Databases are used by businesses to record routine transactions like paying suppliers, fulfilling orders, monitoring customers, and paying staff. Databases are also necessary to give data that will improve decision-making by managers and staff and help the organization run smoothly. If a business wants to find out which of its product is the most popular or who its most profitable client is, the solution is always in the data. That is the end of the first half of the chapter. Thank you.